Okay, suggestions for homework problems we should talk about. Besides 27 through 29. So I know about those. Someone said 14. What else? Other suggestions? Is it 12? Did I hear 12? Is that right? Any other suggestions? Last chance. So just 12 and 14? 10? Okay, take a look at these. Are there any others? 10C, 12, and 14. So vote for your two favorites. Once you know your two favorites of these, 10C, 12, 14, go ahead and get your heading on and pass it in. Okay, should we vote all in favor of 10C or just 10? Okay, 12. All in favor of talking about 12. 14. Okay, so we'll just do 14. It's the only one that had any response. Okay, hopefully hopefully should have been easy, okay? If this angle is 2.1 radians, what does that mean, 2.1 radians? So what's the bridge between these distances, arc lengths and radius, and these angles and radians? There's a really important bridge. What's the important bridge? Right. So radius lengths. So what does 2.1 radians mean? Not quite. 2.1 radians. What is that? Okay, yeah.
It's sub-10s on the arc length is 2.1. The length of 2.1 radius.
Yes, exactly. So it's an angle that subtends an arc of 2.1 radius lengths. So then we look at this picture, and then how do we interpret this picture? If this angle is 2.1 radians, then it subtends an arc length of 2.1 radius lengths. How does it help us with this picture? Well, yeah, so S is 2.1 radius lengths. And each radius length is what? 7 inches. So S is going to be 2.1 of this distance right here. Or, yeah, 2.1 times 7. So S is 14.2. So the bridge between these angles and these distances is radius lengths. The number of radians is the same as the number of radius lengths subtended or cut off by the angle with that radian measure. Okay. This one. So here we've got a radius of 2.4. And the arc length is 9.8 centimeters, and it's asking for theta in radians. How are we going to get theta in radians? It's just understanding what radians are. Theta radians will be the angle that does what? Subtends an arc length of theta radius lengths. So 9.8 is the same as theta radius lengths wrapped on the circle. So we need how many, we want to know how many radius lengths is 9.8. How many radius lengths is 9.8? How would we find that? If each radius is 2.4 and we got 9.8 centimeters? Yeah, we're going to take the length of the radius, or take the total length of the arc, and find out how many radius lengths are in it. So it's going to be 9.8 over 2.4. That'll be the value of theta. What does that equal?
4.08.
Thank you. 4.08. Now it also asks for that in degrees. So to get from radians to degrees, what's our intermediate step? What do we find first? To get what? Yeah, so let's just figure out what percent of the circle is that. So to get that percent of the circle, we're going to divide by the total, the whole rotation in radians. So that will be the fraction of the circle that we have that we're subtending. That's the fraction of the circle that we're subtending. To get degrees then, we want that same fraction of what total amount? Yeah, so we want to take this, this is the fraction that the angle is subtending, our 4.08 radians over the total number of radians. So we want to take that same fraction, or that same percentage, of a total of 360 degrees. And that'll give us degrees. Questions on part B? Part C. So now it gives us 81 degrees and an arc length of 10.8 and asks us to find the radius. So do we have a straightforward relationship between degrees and arc length? No. What's our connection of arc length to angle? Radians. Okay? So what we'd like to do is get 81 degrees. If we can get that as radians rather than degrees, then we're home free. Because then we have kind of apples to apples here. So we got 81 degrees. And we want to convert that to radians. Intermediate step. Yeah, find the fraction of the circle, percent of the circle, and then get radians. What percent of the circle is 81 degrees? How'd you get that? You're going to take the portion over the whole, and that gives you the fraction of the circle that we have. We have 81 3/60ths subtended of the circle. 81 3/60ths subtended, and we want that same fraction of what? So this is our fraction of a full circle. And we're going to take that same fraction of what to get radians? Yeah. Take that same fraction of a full rotation of radians, and we'll get the corresponding fraction of radians. So I think that turns out to be 0.45 pi, if I remember correctly.
Yeah, it's like 1.4.
Okay. So now I've got, instead of 81 degrees, I've got it in radians. I'm writing it as 0.45 pi. And so here we have feet. And so how does 0.45 pi relate to this arc length? .45 pi, how does it relate to that arc length right there?
That's how many radius lengths would be.
Exactly. Because it's the radian measure, it's also the number of radius lengths subtended. So 4.55 is the number of radius lengths. And 10.8 is that corresponding number of feet. So we need to set, and we're trying to find the length of one radius. So to get radius lengths, we could take the 10.8 feet and divide it by the length of one radius, and that would give us the number of radius lengths. And we could solve for r. So we've got the number of radius lengths, and we could also set up that the total arc length divided by the length of one radius would give us how many radius lengths it would be. So those two would be equal. So then r would be 10.8 divided by 0.45. 0.45 pi. And what do you get? 7 point something? 6. 4. Okay, anybody have a question? So notice how I didn't use any formula. I just reasoned everything and just understanding percent and division, right? And I could reason my way through the whole thing there. I didn't need to memorize any formula. And that's always what we're encouraging, because memorizing a formula, it doesn't work if you forget the formula. But practicing reasoning works in all kinds of situations, right? And it empowers you, okay? It empowers you. So as much as you can reason through solutions rather than trying to memorize steps and formulas, you're going to be better off. And that's what we're trying to encourage in the course. Any other questions on the homework? Okay, so we've been working, last time we started working on the bug on the fan, and the fan has a radius of 2.6 feet. Okay, and so we're talking about quantities that we would need to track the position or pinpoint the location of the bug. All right? And so we've been talking a lot about angle, so the angle is real important. So the first quantity is so just saying angle, remember back from the first week of school, just saying that the quantity is angle is not nearly specific enough, because we could define dozens of angles in this scenario. So what particular angle are we talking about did we just define? So what was one more piece of information associated with that angle? Okay, so from 3 o'clock? What else? Angle swept counterclockwise. And so when you see CCW or CW, this means counterclockwise or clockwise. That's our shorthand. So angle swept counterclockwise from 3 o'clock. What else? We want to use radians. Okay? And so this is what we're going to call theta. Greek theta is the kind of the convention for representing an angle. Okay? What was another quantity that we wanted to track or monitor? So we introduced these things, a horizontal diameter and a vertical diameter. So how did those help us pinpoint the position of the bug? Okay, positive or negative. So what quantity are we talking about? So someone up here was saying it. So like the horizontal diameter, what quantity is associated with the horizontal diameter that helps us locate the Yeah, so if it's distance from the horizontal diameter, like this right here, so we could say distance above horizontal diameter more specifically vertical distance, so vertical meaning straight above, vertical distance above the horizontal diameter, and then we're going to track that in feet. So what's the maximum value that that quantity can attain? The vertical distance above the horizontal diameter in feet. What's the maximum value that quantity can attain? So I heard some different things there. If the quantity is the vertical distance above the horizontal diameter measured in feet, what's the maximum value that that quantity can take on? Doesn't it occur right there? And what would the value of the quantity be right there? More people are saying it now. 2.6. There were some different answers, but this is 2.6, right? If we're saying in feet, the maximum quantity or the maximum value that quantity can attain is 2.6. Okay. What was the other quantity we wanted to look at? Uh-oh. Going backwards. Horizontal distance to the right of the vertical diameter. Okay, so from now on, we're going to do some acronyms here. This is going to be VDAHD. Okay, good question. So why are we saying vertical distance to the right of the vertical diameter? So it's so that we can distinguish, right? So we can distinguish. If what's that? You figured it out? Okay, but your question still stands?
Yes.
Yeah. Okay. So we want to be able to numerically distinguish between being to the right and being to the left. So by saying it's the horizontal distance to the right, how does that numerically give us a distinction between being on either side? Positive and negative, right? So if we're to the right, that would mean going to the right would mean increasing. So over here, those quantities would be just positive and negative, right? So over here, the horizontal distance would be positive, and over here it would be negative. So that's why we specify right, because we're specifying where it will be positive. Okay, so the vertical distance above horizontal diameter in feet, VDAHD, okay? And then this one will be HDRVD. So I may use those acronyms, so don't forget what that means. So vertical distance above the horizontal diameter, or horizontal distance right of the vertical diameter. It doesn't mean I'm diagnosing you with something, okay? And this is in feet. What's the lowest value that that second quantity can attain as the bug is moving around? Where will that occur? So tell me an angle. How about an angle? Where will that occur? The lowest distance of the lowest value of that horizontal distance. High radians, good. At the left edge, and what will the value be? Negative 2.6, right? Right there, that second quantity will be negative 2.6. That's the lowest value it will attain. Okay. Any questions on that kind of setup? Now we're going to really pick it apart here. Where are we? So how do we're gonna stick with our vertical distance first. Okay, vertical distance above the horizontal diameter and the angle. So we got those two quantities, theta and our vertical distance. How is it that what is our strategy for looking at the covariation of two quantities? Remember doing this? What's our strategy for modeling or kind of analyzing covariation between two quantities? What our strategy was a couple weeks ago? Okay. Changes in which?
You have a little change in x.
And what will our x be like this time? What's the quantity? It's x.
The distance above the horizontal axis.
Is that what our input is? So x is like input, right? It's like the one we have control over. So what's that going to be? Kind of giving you a hint here. Yeah, that's going to be our angle. So our input quantity is going to be angle. So we're going to, like he said, we're going to look at little increases in angle. In this case, I'm doing 1/16 of a circle each time. So we're going to go by 1/16 of a circle for our angle. And as we do that, what are we going to look at? Do you remember? What are we going to think about? Okay. So first, we're just going to ask. I've got this written out here. Let's move this out. There we go. So our input quantity is going to be our angle swept counterclockwise on the positive x-axis, and my increment's going to be 1/16 of a full rotation. That's going to be just like this. 1/16 at a time. Okay? And then we're going to ask for each time we increase the angle by that much, we're first going to ask about the output. We're going to say, did the output increase or decrease? That's the first question. And our second question is going to be, what about the changes in the output? So we're going to compare the current change to the previous change. And then we're asking, how are those changes changing? Are those changes increasing or decreasing? And to help us answer that, remember we talked about this, are the changes becoming more positive, more negative, less positive, or less negative? And that helps us answer the question, are the changes increasing or decreasing? And our third question was about the rate of change then. Once we answer this question about how the changes are changing, then it helps us to conclude what the rate is doing, how the rate is changing. Okay? So our output, like I said, our output quantity is going to be vertical distance above the horizontal diameter in feet. Okay, vertical distance above horizontal diameter in feet. All right. So I'm going to make my first change in angle, and we're going to ask. So let me just show you how I'm displaying this, and let you see what's going on here. Okay, so I just first see how is it that I'm representing the output quantity in this illustration, and how am I representing changes in the output quantity? So I want you to talk to the person next to you. Where should you look here in this diagram to see how I'm representing the output quantity, the height, and then where should you look to see changes in the height? Go. Everyone's talking to somebody. What should you look at to see height, and what should you look at to see changes in height? Okay, so what are we looking at in this animation to see the output quantity of vertical distance above horizontal diameter, or height? Where are we looking? He said the red line. Agree with that? Is the red bar showing the height of the bug, or the vertical distance? Yeah, the red bar is showing the output quantity. Where do you look to see changes? Yeah, so over on the right there, I'm showing, the dots are showing intervals that are showing the changes in the height, okay? So, first increment of the angle, what does the vertical distance do? Does it increase or decrease? Of course it increases, right? It increases. And actually, let's talk about this like kind of one quadrant at a time. So this first quarter circle is called the first quadrant, all right? So in the first quadrant, what does the height of the bug do? It goes from what to what? 0 to 1. Agree with that? Vertical distance above the horizontal diameter in feet goes from 0 to 1. Not quite. What is the starting value? What's the vertical distance above the horizontal diameter? 0. What's the vertical distance above the horizontal diameter? Here. Yeah, in feet, it's 2.6, right? So in the first quadrant, the height increases from 0 to 2.6. All right, and so we're going to, I think this is on the next page of that. You can make these graphs. Where's this? We're basically on page 274. We're basically creating that graph on the top of 274, and maybe not asking the exact same questions or doing it a little bit differently, but the idea is to create this graph of vertical distance versus angle swept counterclockwise from 3 o'clock. Okay, so our horizontal axis is going to be theta, and I'm going to start by doing theta as just portion of the circle. So here's the first quadrant will be 1/4 of a circle, and then we'll go to 1/2, and then 3/4, and then 1. What is that? Yeah. So what quantity am I measuring across the horizontal axis here?
The distance from the starting point.
Is it a distance? Is that what kind of quantity I'm measuring? Is it circumference?
Number of times around the circle.
It's an angle, right? This is angle, and I'm measuring the angle in what unit? Is this radians? Nope. What is it? So what unit is that? What angular unit is that?
Circumferences.
Yeah, percent. So it's like fraction or percent of the circle. We said all angles are based on percent, so I'm going to actually use that. I'm going to actually just use what fraction of the circle have we rotated here. Okay? So, and then someone said circumferences. That's okay too, right? So it's the same. Percent or fraction of the circle. All right, and so at 0, at 0% of the circle rotated, what is the vertical distance? It's 0. And we said in the first quarter circle, that vertical distance goes from what to what? 0 to 2.6. So at 1/4 circle, well, we're up here at 2.6. So this is going to act as our axis as well. Okay, so here we are. So the question is, how does it get there? How does it get there? That's where the changes come in. Okay, so in the first 16th, we said that vertical distance increases. Okay, and so it puts us right here. So I'm going to take the next change in angle, 1/16. What happens to the vertical distance? Increases. What about that change in vertical distance compared to the previous change? Less, right? It's a less positive change. What about the next? We'll do it one more time. Advance the angle 1 more 16th of a circle. What happened to the height or the vertical distance? Increased. What about the change in vertical distance? Less positive, so it is. The changes are, he said decreasing. Agree with that? Yep. The vertical distance is increasing in this first quadrant, but those changes in vertical distance, you see each change is they're decreasing. So, do we get a straight line from here to here? No, the first change is the greatest. But then the next change is a little bit less. And then the next change is less even still. So we have an increasing quantity, vertical distance is increasing, but the rate is doing what? Decreasing because the changes decrease. The changes decrease. Okay, so I'm just gonna do this several times. Show you the next quadrant. You can talk to the person next to you and discuss. In that quadrant, what does the vertical distance do? It goes from what to what, and therefore does it increase or decrease? And then, what about the changes? What about the changes in vertical distance? Are they increasing or decreasing? Go. So talk about that. This is not trivial. This is not, second quadrant's not simple. Okay? So, 2 questions. What's the vertical distance doing? What are changes in the vertical distance doing? Go. Okay, so the vertical distance changes from what to what? Someone said 2.6 to 0. Some people agree with that. Everyone agree? Starting value of the vertical distance is 2.6. Final value? 0. That's right. Okay, so we're starting up there at 2.6, and our final value when we get halfway around the circle is going to be 0. So now the changes. The first change, is it a positive or negative change? Is it a relatively large positive change or relatively smaller? Sorry, is it? Once again, the changes, that first change, positive or negative? So from the first position to there, is that a positive change or a negative change? A negative change. Is it a relatively large or small negative change? Relatively small. So then each subsequent change becomes what? More negative or less negative? More negative. They're larger and larger negative changes. So are those changes increasing or decreasing? If they're becoming, those changes are becoming more negative. So I'm hearing both. So I told you this isn't trivial. And we've done it many times and it's still confusing. More negative changes, are they increasing or decreasing? So here's an example of values that get more negative. Negative 1, negative 5, negative 12, negative 50. All right? That's an example of the changes. The first change was a change of negative 1, then negative 5, then negative 12, then negative 50, as an example. Is that sequence of values increasing or decreasing? Decreasing. More negative means decreasing. So those changes get more negative, so those changes are decreasing. So what about the rate of change? It's decreasing. All right, and so if we map out the points, we get a small negative change to start, but then with each subsequent angle, we get a larger negative change. Okay, not my best. But you get the point. Yeah, no, so let's do better. Slightly better. Okay. So the vertical distance is decreasing and the changes are decreasing. So the rate of change is decreasing because the rate or those changes are becoming more negative. Okay, next quadrant. Talk about it. Go. 2 questions. Okay, so the vertical distance goes from what to what? 0 to negative 2.6, agree? 0 to here down at the lowest point, negative 2.6. And is that an increasing or decreasing value of the vertical distance? Decreasing, right? It's at 0, it's going to decrease down to 2.6. Now what about the changes? The first change, negative or positive change? Relatively larger or smaller? Relatively larger. And so those negative changes become more or less negative? They're becoming less negative. They're negative changes becoming less negative. So those, is that increasing or decreasing changes? I heard both. If they're becoming less negative, then those changes are increasing changes. Okay, and so then if I plot the points with increase, so the rates, sorry. So the vertical distance is decreasing, but those changes are, there's the first change. So there's the first change from there to there. Then they're becoming less and less negative. So that's increasing. Values that become less negative are increasing. Okay? Last quadrant's the easiest. Go. Last quadrant. Vertical distance goes from what to what, and then what do the changes do? Vertical distance goes from what to what? Negative 2.6 to 0. The changes, which of these four do the changes do? Are they positive or negative changes? Positive changes, becoming more or less positive. Those changes become bigger positive or more positive. Therefore, the changes are increasing. Changes are increasing. Okay, so what are we doing? So we're tracking just a big picture here now. We've tracked the vertical distance of the bug as it made one full rotation. So one full rotation and angle, we lay it out horizontally on the axis here. So this is going around the circle, right? Going around the circle and then the y quantity is showing the vertical distance of the bug as we go around the circle. So what does it do? In the first half of the circle, it goes up to the top and back down to the middle. Second half of the circle goes down to the bottom, back to the middle.
In theory, isn't that just exactly the two halves of the circle if you kind of put them?
Okay, I'm glad. I was just about to mention that. So, although we're tracking circular motion, these curves are not circular. They're not. In fact, I'll show you exactly what they should look like. Here we go. So here's what it truly looks like. And those are not circular curves. Yeah, it's not circular curves.
Out of curiosity, why isn't it circular?
Because we took the circumference and we straightened it out. See? See, so we went around the circle, but we did that as a straight line like this. And then we measured the height as we did that. So it's no longer circular. Okay, so right now, the max value, tell me again what it was? 2.6. And our lowest value of the quantity? Negative 2.6. And so how could we write out these angles? We did it before as percent of the circle. Let's now do it as radians. So what angle is swept out to get to the high point of the circle? And this is back to the middle on the far left end of the circle. And this is the bottom of the circle. So what angle swept out gets him to the top? Half of a circle, right? And then back to the midline. And then down to the bottom. And then all the way around is our 2 pi. Okay. We could use any that we want here. We could use degrees. What would it be degrees? 90, 180, 270, 360. Okay? There's another way we can label this axis as well. So rather than use feet, what else could we choose to use on this axis? That's another way we can measure how far up or down the bug is. Yeah.
Arc lengths,
Um,
or just radians.
yeah, radius lengths. Radius lengths. So how many radius lengths would the bug attain up here? That's one full radius length. And then what about when it gets to the bottom? -1. Okay. What's the advantage to that? Why is there an advantage to changing that scale from feet to radius lengths and going only from -1 to 1? Okay, so I heard some different things, but I think someone said it can, and now it can mean any circle, and that's true. So we could have a circle of 100 meters, and we could still represent it with radius lengths, and the top of the circle would still be 1, and the bottom would still be -1. Okay, so this is so using radians and using radius lengths as output makes a very special function. So let's write it down. So the input of the function is the angle swept counterclockwise from 3 o'clock. Okay, in radians. And the output is our vertical distance above horizontal diameter in, what did we say? Radius lengths. So when you have those exact input and output, angle swept counterclockwise from 3 o'clock, and vertical distance above the horizontal diameter in radius lengths, you get a very special, important function. Anyone know what it is? This is what the sine function is. Okay, now the blue function has the same input. The one that we created has the same input. And the output how's the output different? It's still vertical distance above the horizontal diameter, but what's the difference? It's in feet. So if this outputs radius lengths and gives us as low as -1 and as high as 1, how could we write a new function g that would give us the right output in feet? So rather than outputting radius lengths above or below, we want to output number of feet above or below. How could we write g of theta? You want sine theta times the radius length. So do you mean like 2.6 times sine theta? Is that what you mean? All right, let's give it a shot. So everyone get your calculator out. We want to look at pi over 4, or 1/8 of a circle. Let me show that.
Is this similar to 27 and 28?
We're getting there, yeah. So yeah, we just didn't make it far enough. So yeah. Okay, so I'm showing the position of the bug when he's gone 1/8 of the circle, which is pi over 4 radians. Okay, so if you in your calculator make sure it's set to radians. So if you hit mode, I think the second or third menu item down there, it's the third one down. Make sure it's set to radians. Go back to the screen, and we're going to do f of. You're not going to do the f of part. I'm just writing that. F of pi over 4 would be, here's what you're going to put in, sine of pi over 4. So everyone do that. Sine, put parentheses around it. Sine of pi over 4. So here's this point pi over 4, and what is the sine of pi over 4? 0.707. So we need to make sense of that number. Why does the number 0.707 as the output of f make sense? What does that number mean? 0.707 what? What's that?
The number of radius lengths above the horizontal.
It's the number of radius lengths above the horizontal diameter, and so why 0.707? How about, why is it a number less than 1?
Because we'll never go over a full radius.
Okay, yeah, so the most the bug will get to is 1 radius length. On the way up, what numbers will it cover?
Everything between 0 and 1.
Yeah, fractions of a radius length. So when we've done a pi over 4, we are like 70% or 0.707 of the way up to the top, which is 1. So his height is 0.707 of a radius length. Okay? So then, what about this one? How, if we wanted to know how many feet it was, how could we get how many feet it was? What's that? Yeah, so it'd be 0.707 times 2.6. And what's that? 1 point, tell me? 84. So the bug is 0.707 of a radius up and 1.84 feet up above that. And so this works right here. You just take whatever fraction of the radius you are, multiply it by the radius length, it'll give you how many feet then you are above the horizontal diameter. Okay, so really important stuff. So that's our base function, and then we can write any function by taking r times sine theta. Okay, we're going to start up with the reading and workbook short assignments again, so look for that for Friday. Need a rubber band?
Yeah.
Okay.
You totally would push it just because you don't like me.
No, I do.
Right?
Just in a different way.
Was you already